Good afternoon, everyone. I'm Carlos Cinelli from UCLA, and this is a joint work with Daniel Kumar, Brian Chen, Yuda Pearl, and Elias Barenboim. So today I wanted to talk to you about sensitivity analysis, or more precisely, like I like to put it, what you can do when your causal assumptions, your usual causal assumptions go wrong. And to ground that, I would like to start with a real motivating example, which was the debate on cigarette smoking and lung cancer that took place in the 1950s and 1960s. So observational studies back then found a strong association between cigarette smoking and lung cancer. They found that smokers had 9 times the risk of non-smokers to develop lung cancer. So this naturally leads to the question, is this association causal? Well, not everyone agrees with this hypothesis. And one of the main opponents of this hypothesis was the world-famous statistician Ronald Fisher. And he thought it was likely that a common cause like genotype could be the explanation of this association. And theoretically, Fisher is right, because observational data alone cannot distinguish between the first model and the second model. So how can we move this debate forward? Well, a critical step in this debate was a sensitivity analysis, and it consisted of the following hypothetical exercise. So first, we're going to suppose for a moment that Fisher is right, that all the observed association between cigarette smoking and lung cancer comes from the unobserved confounding. Now we're going to ask ourselves the following question. How strong would this unobserved confounding need to be to explain all the association we see? And that was what Cornfield computed. And they find out that if smokers have 9 times the chance of non-smokers to develop lung cancer, and this is not because there is a causal effect between cigarette smoking and cancer, then this has a logical conclusion, which means that an observed confounder like genotype or hormone has to be 9 times more prevalence in smokers than in non-smokers. And experts at the time said there is no way there is a gene or a hormone which is tightly linked to cigarette smoking as this one, as 9 times, so this is implausible. So the logical conclusion here is that an observed confounding cannot account for all the observed association, and there must be a causal path between cigarette smoking and lung cancer. So to summarize the story, why do we need sensitivity analysis? Well, causal inference requires untestable assumptions about the data generating process, such as the absence of certain direct causal relationships or the absence of unobserved common causes between certain variables. Therefore, conclusions based on causal models are provisional. What if these assumptions are disputed? So sensitivity analysis allows us to quantify how the violation of assumptions affect our conclusions, and we can submit these results to expert judgment to decide whether problematic degrees of violations are plausible. And how is the current state of sensitivity analysis literature? So sensitivity analysis has been extensively studied in the health sciences, economics, and statistics. However, the current literature is limited to specific model structures and solved on a case-by-case basis. For instance, we have separate results for backdoor identification, for instrumental variable identification, for mediation analysis, and so on. So can we move from this case-by-case approach and have a general-purpose algorithmic framework that capture all these canonical cases and many more? So this is the contribution of our paper. So in this paper, we develop a formal systematic approach to sensitivity analysis for arbitrary linear structure causal models. We start by formalizing sensitivity analysis as an identification problem with non-zero constraints. We then devise a novel graphical procedure to incorporate numerical constraints on bidirected edges. We call this procedure push forward. And we finally develop an efficient graph-based identification algorithm to derive sensitivity curves. So not only were we able to capture these canonical cases, but we run an exhaustive set of experiments that show these are a small subset of all possible sensitivity analysis covered by a framework. So, of course, I cannot show details in a 4-minute talk, so I hope I got you interested. And if you want to learn the details, please come by our session tonight. It's poster number 78, and thank you.